Hello, through the Virtual Immersion in Biomedical Engineering program, our group worked to design a non-invasive glucose monitor for diabetic infants in low-income environments. Shown here are the group members of Team 17C. Neonatal diabetes mellitus causes infants to be unable to produce enough insulin, leading to elevated glucose levels. The current method for glucose monitoring is expensive and is invasive for infants, emphasizing the need for innovation. We aim to create a cheap and non-invasive infant glucose monitoring system for hospitals.
To make sure we chose the best solution to our problem, we made a P chart. Based on the P chart, we concluded that the best solution was analyzing acetone levels in breast samples. In order to monitor diabetes in infants, we will measure the levels of acetone in exhaled breath. Acetone is a great way to monitor diabetes, and it is a ketone that is produced when fatty acids are used instead of glucose to produce energy. This leads to elevated levels of glucose in the body. In general, elevated levels of acetone are found in diabetic patients.
The general design of our breast system to monitor glucose can be broken into three parts: collection, made up of a mask and tube system; storage, utilizing a vacuum chamber; and detection, comprising electrical, sensing, and processing components.
Our collection method works by collecting air through a repurposed CPR mask in a plastic bag. The CPR mask has two one-way valves to facilitate breathing to collect all air. The first valve faces inward so that the infant can still breathe. The second valve is faced outward so that all air leaving is directed into the bag. Most air collection is done with Tedler bags, but those can be expensive for single use. The LDPE bags have been shown to have the same effectiveness for a cheaper price.
This is our storage device. On the left side you have a sketch, on the right side a full 3D render. The main body of the device is going to be made up of 5 acrylic panels connected using silicone adhesive. These two holes will be connected using a vacuum pump to blow air from the inside chamber through an HEPA filter to filter contaminants. Up here you have a vacuum gauge to determine when a sufficient vacuum has been reached, and this tube will be used to attach sample bags to introduce sample air into the internal chamber. This small square is where our sensors will be placed, and these two holes will be humidity trapped to regulate the humidity level. This screen right here will be used to display the values described by the code, and the bottom box will be made out of stainless steel.
Here is our 3D detection model. All these internal components are wired through a breadboard and Arduino system. Inputs from the air in the vacuum chamber are collected through humidity and acetone sensors. Then inputs are processed through the Arduino, which is powered by a 10-volt battery-operated power bank. The microcontroller has a preloaded data processing program which uses equations from studies outlining a conversion from acetone to glucose. A code then interprets and displays glucose results on the LCD screen.
This is a flow diagram showing all the actions and decisions made by our code. We're first going to read out the acetone humidity levels in the chamber, then regulate that humidity level using a humidity trap. We're then going to see if a switch has been flipped, sending us either into an English or language inclusive mode. Both modes are first going to transfer the acetone level to a glucose level, and then check if the glucose level is at a diabetic level displaying a red light, a uncertain level displaying a yellow light, or a safe level displaying a green light. The English mode is then to display all of those in English text, and the language inclusive mode is then to use only standardized scientific symbols. Both are then going to display the glucose level as the final step.
To make sure our device is safe to use for infants, we will follow safety regulations and standards set by the ISO. The first standard makes sure that the medical device is safe throughout its lifespan. The second standard makes sure that the software and code is up to date and safe to use. The third standard makes sure that the air samples collected are not contaminated. The fourth sample makes sure that the materials used are safe for infants. And the final standard makes sure that the gas pathways do not contaminate the samples collected.
The base cost for a glucose test is 98 cents. Our system price is $250. So if our system is used only 10 times per day, our average cost per test over a 1-year period would be 7 cents. This is both conservative estimation of how many times it would be used and how long the device would last. Given the low price and long lifespan of our device, the Neo knows it's cost effective.